Okay?
There we go.
Awesome.
Okay, so next we're going to hear from Wang. Hot Jupiters are dynamically hot. Hot Jupiters around hot stars are dynamically hotter.
Okay, awesome. Hello, everyone. I'm Wang, assistant professor at Indiana University. Today, I will summarize our recent observational developments on hot Jupiter architectures and their relation to host star properties. I hope this will help us move towards a more unified understanding of hot Jupiter formation. So although the discovery of hot Jupiter surprised the community, but if you look at the overall Jupiter occurrence rates along the semi-major axis, which is consistent with the first order, like our conventional understanding of hot Jupiter formation, the cold Jupiter is much more common than hot Jupiters. For decades, the community trying to figure out whether this short period Jupiters are leaking from this cold Jupiter reservoir. If so, what mechanism dominates the leakage? So in the first part of my talk, I will review the two aspects of hot Jupiter configurations and argue hot Jupiters are dynamically hot. So let's begin by examining the isolation of hot Jupiters. What fraction of these planets are in compact multi-planet systems? Over the past decade, it has become widely accepted that hot Jupiters are typically isolated. This view was largely influenced by this study in 2012 by Stephen et al., which analyzed Kepler data, and this result was later confirmed by Wang et al. 2016. They plot all Kepler Jupiters and connect planets in the same system. As you can see, hot Jupiters with no nearby companions are isolated. Warm Jupiters often have additional nearby companions. Thanks to extreme precision photometry, space missions helped us detect the first several exceptions, including the remarkable VAS-47 system. However, more recently, a statistical analysis from the TESS survey has again confirmed the prevailing view on this topic that hot Jupiters are still isolated. But we need to keep in mind all the results we talked about are based on the transit survey, which has inherent biases. They cannot detect planets that are too small or not transiting. That's why we turn to the transit timing variation, or TTV method, to estimate to get a more precise estimate of the occurrence rate of hot Jupiter with the nearby companions. So actually, Stephen et al. 2012 has analyzed the precise Kepler data and didn't detect any TTV in hot Jupiters, but their work was limited by the fact that at that moment, Kepler only observed for 6 quarters, which is about 1/3 of entire mission duration. To address this, we revisit the Kepler TTV and did a similar analysis, but using the complete Kepler data. So in our analysis, we identified total 16 validated TTV signals, and 2 on hot Jupiters and 14 on warm Jupiters. By applying the injection and recovery test to correct for detection completeness, we converted these detections to occurrence rates. So we found at least 12% of hot Jupiters and 70% of warm Jupiters have additional nearby companion in the same system. So this result was further and well supported by the current result as TESS continues to detect systems with hot Jupiters in compact multi-planet system. So to summarize the first part of the talk, although our analysis show that hot Jupiters are not as isolated as one thought, but they are still much less likely to have additional nearby companion compared to warm Jupiters. So this leads us to the first order picture of the Jupiter configurations, that hot Jupiters are dynamically hotter than warm Jupiters. So let's turn to the second important aspect of exoplanets, spin orbit misalignment, also known as stellar obliquity. Famously, 2 decades of RM measurement tells us some hot Jupiter are spin orbit misaligned, but whether this misalignment can be used as a reliable indicator of their dynamic temperature of the systems are highly debated, because one category of theorists believe that misalignment can be primordial or universal, which will affect all types of planets. In this, based on this view, even the system are dynamically cool, they can also be spin orbit misaligned. The other category of theory believes that misalignment is a result from the high E-migration, which will only affect hot Jupiters. So a best way to distinguish these two scenarios is to get RM measurement for different type of planets beyond hot Jupiters. Here you see a plot of all exoplanets on this period versus mass diagram, and I highlighted the RM measurement in color. As you can see, almost in the past, almost all the measurements are on hot Jupiters. It's just because they are easy to observe. So for a long time, there are a very limited number of non-hot Jupiter planets suitable for around bright stars, suitable for detailed follow-ups. So that's exactly the goal of TESS mission, to find right target suitable for follow-up studies. So taking advantage of TESS target, Melina Rice and I started this source project to expand RM measurement to different types of exoplanets, including warm Jupiters. I have highlighted all the targets we observed. So we conduct numerous observations for warm Jupiters, and several undergrad students finished their first publications with us. And our postdoctoral researcher, Xianyu Wang, recently published a new statistical studies, which includes additional 6 warm Jupiter systems. As you can see from the RM effects, they are all spin orbit misaligned. Sorry, spin orbit aligned. So if I plot all the current node Jupiter misalignment along the normalized semi-image axis, you can see here all the hot Jupiters are sometimes misaligned, but warm Jupiters tend to be aligned. So to summarize this part, the second key message I would like you to take away is that the dynamical hotness of hot Jupiter extends from their companionship to the misalignment. Hot Jupiter are sometimes misaligned, but warm Jupiter tend to be aligned. So this result strongly argue against the primordial misalignment. If the misalignment is universal, the warm Jupiter can be misaligned as well. So to summarize the first part of talk, let's return back to the occurrence rate plot we discussed at the beginning. It looks like, based on current observations, hot Jupiters are primarily dynamically hot. They are more likely to be isolated and sometimes spin orbit aligned. And warm Jupiter, in contrast, are more likely to be found in compact multi-planet system and spin orbit aligned. So a straightforward explanation of this trend is most of warm Jupiter form either in situ or via disk migration. In contrast, most of hot Jupiter should form through high E-migration. Since our obliquity study exclude all the binary systems and stellar quasar is not an option anymore, so we believe in single star system, high E-migration should be triggered by planet-planet interactions. So planet-planet interactions, as Jesse just discussed, depends on whether you can form multiple planets in Jupiters in the same system. And famously, Jupiter's occurrence rate is related to the host star metallicity or stellar mass. And based on this view, we expect that system with massive or metal-rich disk can form multiple planets, multiple Jupiters, and can trigger the dynamical instability and lead to the dynamic hot properties. So this argument provides us an alternative explanation of this temperature lambda relation. This was originally attributed to the tidal damping. So hot Jupiter can be misaligned around both cool star and hot star, and only cool star can be realigned because of a, say, convective envelope or radiative core. And as you can expect, if the tidal realignment story were correct, you expect the aligned system should be older than misaligned ones, but observations suggest the opposite. It looks the exoplanet system should be formed in a aligned state, and misalignment, they develop misalignment over time rather than gradually becoming aligned. So our suggestion is this misalignment probably is caused by that dynamical instability, and over time, the system will develop misalignment through the planet-planet interactions. So another piece of tentative evidence to support this is that the misalignment rate is not level off at a craft break. It actually increases with the stellar temperature. This was first pointed out by Albert's review paper, and basically early F-type stars are more likely to be misaligned than late F-type stars. So since orbital inclination and eccentricity are basically the two aspects of a dynamic temperature, and one can expect they related to stellar properties in the same manner, but actually they are not. The temperature, as we just discussed, so the obliquity related to stellar temperature, but previous studies suggest the eccentricity related to the metallicity, which is very puzzling. And we went back and re-examined the metallicity and eccentricity correlation, and we found even if we use this arbitrary cut, like solar metallicity as an arbitrary cut, that two groups are not a significant difference from each other. But if we check the stellar Jupiter eccentricity as a function of the stellar mass, we actually found a very strong correlation. The Jupiter are more likely to be eccentric around massive stars. So to summarize the second part of my talk, we found the evidence that hot Jupiter are more likely to be misaligned around hot stars and more likely to be eccentric around hot stars. And actually, they are more likely to be isolated as well, as you can imagine, as the eccentricity and inclination increase, the likelihood of the Jupiter becoming the only planet in the inner system also increase. We find 7 out of 8 hot Jupiter with nearby companions are around relatively low mass star. And since I'm running out of time, I will leave my conclusion slides here and happy to take questions.
Thanks, Simon. Early career photos.
Hi, Shashank Dalakia, University of Queensland. Could you go back to the result about the TEF a couple slides ago?
Sorry?
The scaling with TEF for the spin orbit inclinations?
The relation with the temperature?
Yeah, I was wondering, so as these stars get a lot more massive, they also rotate much more rapidly, but the stars that we're actually sensitive to with the Roster-McLaughlin have to be within a certain range of rotation rates. So do you see a bias there where you're more likely to see sort of pole-on stars and therefore more misaligned planets around those stars, around the hotter stars?
So why do you think there is a bias? I didn't fully catch that.
Oh, with the RM measurement itself, because the very rapidly rotating stars are hard to follow up, hard to confirm, hard to...
Oh, that's actually the opposite, because a hot star, and they are very rapidly rotate, the radial velocity precision is very bad, so we need to use the Doppler tomography to get them. So it's harder to measure the super hot star measurement, actually.
Okay, thank you.
In the middle here.
Thank you for the great talk, Ray Holcomb, UC Irvine. I was wondering about if there's been much work done to quantify the RV completeness of searching for smaller companions around these hot Jupiters. You know, their RV signals are so big that you only need a handful of points to say, yeah, there's definitely a hot Jupiter there. But then this question of like how many more smaller non-transiting planets could be hiding, and do we have a sense of our completeness there?
That's a very good question. Actually, if you look at 51 Pack B, and one of our undergraduate students did a test on this. So if you look at 51 Pack B, you thought it's already observed to death. But actually, most of currently known, if you insert most of currently known exoplanets, small exoplanets, right, Kepler planet into 51 Pack B system, based on current radio velocity, we cannot recover that. Just detecting super Earths by using radio velocity is not very easy. So I think there is a huge possibility that the fraction of hot Jupiter with nearby companion can increase since they are not transiting and they are a little bit further away to produce any TTV signals.
Okay, that'll be helpful. Last question. Thank you very much, Sanyu.